All right, today we're going to be focusing on the gas law. So this is our new kind of math. I'm just going to do this again. All right, so today we're going to be focusing on the gas laws. This is kind of our new content for this chapter. When we think about gas laws, what we are really going to be working with is a particular type of equation, trying to understand how gases behave and using these equations to predict how gases are, what they're going to do in the future. This is just one thing to take into account when we are doing problems, when we're doing, reading the word problem and trying to figure out what goes with what. Both sides of the equation are talking about the same sample of gas with the one variables before change and the two variables being afterwards. So when we look at our equations, a couple of things to keep in mind: that anytime we do a word equation, it's always helpful to write out the before information and the after information. And the last thing that you want to do is highlight it here to make sure is that your units need to match and that our temperatures must be in Kelvin. So there are going to be instances, say with pressure, where we're going to have to convert them, and with temperature we're going to have to add 273 to convert it into Kelvin. The gas laws that we're going to be looking at, you do need to know. The first is Avogadro's law, and this relates to the amount of gas in terms of moles to its volume. So this V1 over N1, this is our before, as denoted by the ones, is equal to our volume over moles after, and that's what the number 2 represents. Boyle's law is similar, except it relates pressure and volume, and Charles' law represents temperature and volume. And you'll notice with all of these laws, with these two variables, there are always other things held constant. For Avogadro's law, temperature and pressure are held constant, which is why they're not in the equation. For Charles' law, pressure and the number of particles is held constant, which again is why it's not in the equation. Now, all of these laws are very particular in that they only work under the environment that is laid out. So Boyle's law only works if temperature and the number of particles is constant. If it's not constant, Boyle's law does not accurately predict. Which is why we have a fourth gas law called the combined gas law. And this actually can be used for all problems. So you don't even need to memorize the other laws necessarily. You do need to know them for the test. But this is the one law that you can use that will do every single problem you're going to do. So for example, the way this would work is this would be our equation. So pressure times volume divided by the number of moles and temperature of our before equals the after, is that if something is held constant, right, let's say volume, so our V1 is equal to V2, well, what happens basically is the volume just drops out of the equation because they're equal to each other, and eventually we're going to be dividing by them. So we can simply just ignore when something is held constant. We can ignore it into the equation. And so if we take that and apply it, then the combined gas law, it turns into the other three laws. So for example, if pressure and temperature are held constant, then we get to ignore them. And what are we left with? Avogadro's law. Likewise, if temperature and the number of moles is held constant, then we get to ignore them and we get Boyle's law. And last, if we hold pressure and moles constant, we get Charles's law. So the combined gas law can help us to arrive at all of these other laws. So let's look at how we actually use this. So you do need to know what the variables are in terms of what P, V, N, and T represent. Remember that our pressure units need to be the same, and temperature must be in Kelvin. So if we look at this problem, what is the final volume of a 0.125 mole sample of gas at 1.7 atmospheres, 1.5 liters, and 298 Kelvin is changed to STP. STP was defined in the earlier notes from last week, I think. So that's going to tell us what our pressure and temperature are, and our number of moles increases to 0.225. So looking at this problem, here's what STP stands for. We need to determine what our before and after are. So as we're reading through this, my 1.7 atmospheres, 1.5 liters, all the way through, this is my before, and STP and 0.225 moles, this is my after. So you'll notice for the equation, I have everything that I need except for one thing. And so how I would solve this is I'm just going to take my information and I'm just going to place it into the equation. So my P1 is 1.7 atmospheres, and I'm just plugging everything in. I don't need to do any temperature conversion because it's already in Kelvin. I don't need to do any pressure conversion because they're both the same unit, 1 atmosphere. So it's just do the math. Multiply everything together, solve for the unknown, and I get a volume of 4.2 liters. Okay, so if I do the algebra and rearrange the equation, this is what I would end up with. Let's look at another example where I go through and it tells me moles and volume, but it doesn't say anything about pressure and temperature. When I have a problem and a variable isn't mentioned in any way, shape, or form, I can assume that they're constant. And if they're constant, then I simply get to ignore them in the problem. And so what I'm left with is volume over the number of moles. So then I can just take my information, I can plug it into the equation, rearrange, solve for volume, and I get a volume of 9.2 liters. And then I can always look, which gas law is this? Volume over number of moles, that's Avogadro's. Let's look at another example. So here we have pressure and volume. So I sort what I have in terms of my before and after. Number of moles and temperature aren't mentioned, so I can assume that they're constant, which means I get to ignore them. So my equation is just pressure times volume. So I plug everything in, solve for my unknown, and my volume is 2.7 liters. And which gas law is this? Oils. And the last one you could probably think of where we're going here. The final volume is 10.5, so and the gas has changed from 25 to 50 degrees. So I have my volume here. Pressure and number of particles aren't mentioned, so my combined gas law becomes just volume over temperature. You do need to remember that our temperatures are in Celsius and they have to be converted to Kelvin. So by just adding 273 to both of those temperatures, this is what I get in terms of Kelvin. So I just plug them into the appropriate spots, solve for my unknown, and I get a volume of 11.4 liters. And of course, this is the last one, which is Charles's law. Okay. So go ahead and pause the video and see if you can do this problem. All right, so in this problem, we're going to have to do something we haven't seen before, in that my pressure is in millimeters of mercury, but I'm given a pressure in STP. So because STP is 1 atmosphere, I can simply just turn that into 760. So this is an example where your units of pressure have to be the same. My number of moles is not mentioned, so I can assume that it's held constant. And so this is what my equation ends up being. And so if I just plug everything into the equation, into the correct spot, I can rearrange to solve for volume, and it equals 14.1 liters. So that's the combined gas law.